So let's start with reviewing something that does come up, but often is forgotten about, which is Gibbs free. So that's going to come up under one dot point within your equilibrium, okay? Because equilibrium does actually have a dot point that asks you about relationships between Gibbs free and spontaneity. So spontaneity is from year 11, which is assumed knowledge. And there is an idea of, relationship between Gibbs free. So here we've got photosynthesis is an example of a non-equilibrium system. Write the balanced chemical equation for photosynthesis. So that one shouldn't give you any trouble. So photosynthesis, of course, takes carbon dioxide, CO2 gas, and water. And you're going to create glucose and oxygen. That's what we need to breathe. Balancing this shouldn't be difficult. That should be quite easy. Of course, for photosynthesis, you should also write in the fact that you're going to use chlorophyll, which will then absorb some light. And there's your mark for that. States, right, equation, balance, states, any catalyst or conditions. Now, you're asked, the following values occur for synthesis reaction at 25 degrees Celsius. You've got a delta H and a delta S. One very common mistake is to not pay attention to the units. So you should note that this is kilojoules and this is joules. So those two numbers are not directly comparable. So just pay attention to that. You want to calculate the Gibbs free energy for photosynthesis at 25 degrees Celsius, and then talk about whether it's spontaneous or not. So remember, Gibbs free energy is equal to delta H minus T delta S, where T is temperature in absolute temperature in Kelvin. Now, delta H is given as 2803. Because it's 25 degrees Celsius, it's 273.15 plus 25, basically 298. Multiplied by delta S, keeping in mind that it's only joules, not kilojoules, then this would be negative 0.212. Now, you've got a positive delta H, which means it is endothermic. You've got a negative delta S, which means it's a decrease in entropy. Both of these are not going to help it be spontaneous. So we will quickly work out the number. Giving us an answer of, excuse me, 2866.20. Kilojoule per mole. And keep in mind, of course, you want to pay attention to significant figures. So you really only have 3 significant figures. So that would then mean we've got 2.87 times 10 to the 3 kilojoules per mole. And the point is, because delta G is positive, therefore the reaction is not spontaneous. And we knew that beforehand from our general knowledge as well, of course, because, well, photosynthesis needed sunlight to help it out. We also know that it's endothermic and that it's a decrease in entropy. And so for that reason, this all makes sense. Okay. Let's run through some basic, easier questions. It asks us for an example of a closed system. Now remember what we said a closed system was earlier. A closed system is a system that allows movement of energy in and out of the system, but traps the matter, basically. The matter cannot move in or out. So the reversible changes of phase of carbon dioxide between aqueous and gaseous in a closed bottle. So that seems good. It's a closed bottle. The reversible changes of water between liquid and gas in a dish of water left out in the sun. Well, if it's left out in the sun and it's a dish, then it's not closed, so that's not okay. The equilibrium system of dissolved CO2, HCO3 minus ions, and H2CO3 in a blood where CO2 is continually exhaled through the lungs. Well, you're losing CO2 then, so that's not okay. The production of phosgene from CO and Cl2, where COCl2 is condensed and is removed as it forms. So since you're removing it, it's not a closed system, and the answer is indeed A. We have, in the next question, magnesium reacting with dilute hydrochloric acid to produce hydrogen gas, and it asks us for the volume. That's not really equilibrium, so we'll just skip it for now. It's just simple calculation, and you should be fine with that. Just use your molar volume. Okay? You create hydrogen, which is a gas, use your molar volume to work that out. Okay. In this question, we've got at room temperature, 0.8 moles of SO2 and 0.4 moles of O2 were introduced into a sealed 10-liter vessel and allowed to come to equilibrium. Between time A and B, the temperature of the vessel was decreased. Okay, so we know that this is a temperature decrease. And they ask us for the value of KEQ at time A. That question doesn't seem to need us to know that it's a decrease. All right, so if we're going to do KEQ, then remember what K is, right? You've got SO2 with O2 becoming SO3, okay? So this will then be SO2 plus O2 to give you SO3. And they weren't very clear about which one they were using. We'll assume it's this one. Now, at room temperature, so that means it's at 298 Kelvin, 0.8 moles of SO2 and 0.4 moles of O2. So let's look at it in terms of number of moles first. And we can draw your ice table. So you've got SO2, you've got O2 and SO3. And at the start, you've got 0.8 and 0.4 and no SO3. And that is confirmed by the fact that your SO3 curve starts at 0. Now we note at time A, the SO3 has gone up to 0.3. So this has definitely gone up in terms of moles, as it says over here, to 0.3. Now, if this goes up by 0.3, this must go down by 0.3. So 0.5, which is again confirmed over here. And if this goes down by 0.3, then this must go down by, well, half of that. So it goes down by 0.15. So that would be your change. Given that these are the changes, you'll have the end amounts of the moles, and 0.8 minus that will be 0.5, which is confirmed. 0.4 minus that is 0.25, and 0 plus 0.3 is 0.3, which is confirmed. So this is the number of moles at this point of time, A. Now, what many students may do at this point is then say K equals, well, SO3, which is 0.3, to the power of 1, all over, well, SO2, which is 0.5, to the power of 1, and 0.25 to the power of a half. But you should probably consider what K is, because K is the concentration of SO3 all over the concentration of SO2 times the concentration of O2 to the power of a half using our coefficients here. So given that, remember this is the number of moles. Okay? And the number of moles is not the same as concentration. And so we will need to change this to concentration. Remember, concentration equals number of moles over volume. And so we need to take the number of moles that we've worked out to then get the concentration. Now, if you're confused about where we got these numbers from, we got the numbers from the fact that these were the changes, and the 0.3 of the SO3, which leads to the 0.3 here and the 0.15 here, comes from the fact that we read the graph. At A, this is 0.3. And that is your SO3 curve. So because your SO3 at A is 0.3 and it started at 0, therefore we know the change is positive 0.3, and from there, everything else follows on. But we now need to actually work out the concentrations. So the concentrations would be everything divided by 10. So when it comes to concentrations, this would be 0.05, 0.025, and 0.03. So it would be more appropriate to sub those numbers in and see what we get. And if we use a calculator, $37.9. Oh, 3.79. That's rather odd. We had 0.03 over 0.5. So that would suggest that, I mean, the closest answer there is B, but having said that, we should probably check out what happens if we use, so we'll just quickly do everything again, but using the equation 2SO2 plus O2 to give you 2SO3. So this means that the K would then be SO3 all squared all over SO2 all squared O2. Now, the concentrations won't change. It's just that the equation has changed. So let's just quickly try this out. And this will give us 14.4. So I think it's quite clear that they intended us to use this equation with an answer of 14.4. So as I said before, the equilibrium constant does depend on which ratios you use. Both are really the same equation as you would think, but because one has been multiplied by 2, the K, in fact, has been squared. So the square of 3.79 is 14.4, and that's going to give you that. But the key message that out of this question that you should probably get, apart from knowing how to do the ICE table and so forth, is the fact that you need to change to concentration. It is not the number of moles, it is concentration. And that is a very common mistake that you want to avoid. So answer 8 is C. Right, moving on, question 9. You have the following statements about equilibrium system changing in conditions is correct. So looks like they're still talking about question 8. So SO3 formation has been favored as the equilibrium shifted to the side with less moles. So we'll write out the equation quickly again, just for reference. So they say the KQ will change. Well, that appears true because you've changed the temperature, and the temperature does depend on that. The reverse reaction is exothermic. Well, that doesn't appear true. So you may know that this is exothermic from general knowledge. That is possible, but because it is part of your content. But the other thing is you can look at this. You've now got more SO3 as a result of a decrease in temperature. So temperature has gone down, okay? And because the SO3 has gone up, according to the graph, that means you've shifted to the right. Now, if the temperature goes down and you shift to the right, that means the system wants to shift to the right to bring up the temperature by Le Chatelier's principle. And so that means the forward reaction is exothermic. That's what you can tell through this deduction here. And that's more or less what we said here. So if the forward reaction is exothermic, then the reverse reaction can't be exothermic. So that's definitely wrong. Now, O2 has been removed from the system. Well, nowhere has it says that O2 has been removed from the system, so that doesn't appear correct. And SO3 formation has been favored. That is true. And the equilibrium did shift to the side with less moles. That is also true, but that's probably not a true statement in relation to the changing conditions, because for A to be the appropriate answer, you needed the change to relate to, well, volume. So you needed the change to basically say the pressure has gone up or the volume has gone down. That wasn't the change though. The change was the temperature of the vessel was decreased, which means A is not really the appropriate answer here. And so the appropriate answer would be B. So these questions are quite similar. So 13, in a reaction vessel, you've got carbon monoxide gas, reacts with hydrogen gas to form the following equilibrium. At a certain temperature, the equilibrium constant is 0.71. What is the equilibrium constant expression for KQ for this reaction? And what does the information say about the relative concentrations compared to reactants? Well, gas, 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 gas. So remember, products over reactants. So it's CH4, H2O over CO. So those will be wrong. And your number is 0.71. So we would suggest that it's not really, favored much. So it's less than 1. So in terms of what they're saying here, then we'll probably favor the reactants, because the products over the reactants is less than 1. So that would be the appropriate answer. What are the optimal conditions for achieving the maximum yield? Well, that means you want to push to the right. Pay attention to the fact that it is got a delta H of negative. Delta H is negative, which means it's exothermic. So that means you want a low temperature. So A and B are out. And we now need to look at the pressure. And if you take a look at the left-hand side, it's got 4 moles of gas. On the right-hand side, it's got 2 moles of gas, which suggests that the right-hand side has less moles. So to go to the right, you want high pressure. And that means D would be the appropriate answer there. Okay. Which of the following statements about reversible reactions in gaseous phase where the forward reaction is endothermic is true? Increasing the temperature leads to the back reaction being favored. That's definitely false, because increasing the temperature leads to the endothermic reaction being favored, which is the forward reaction here. The forward reaction is more sensitive to changes in temperature than the backward reaction. That looks good, because the endothermic reaction is generally more sensitive to temperature. Increasing the pressure by an addition of a inert gas leads to the reaction that produces fewer particles being favored. No, it doesn't, regardless of that. Expansion of the volume always leads to a shift in the equilibrium. And no, it doesn't again, because if you don't have gases, the volume doesn't matter. And if the gases do have the same number of moles on both sides, then again, it won't matter. So quite clearly, B is your appropriate answer here. This question should be quite self-explanatory. Okay. Both mass and energy transfer across the boundary is called an open system. You've got a relationship between KQ and temperature for an exothermic reaction. Now, we discussed earlier, for an exothermic reaction, as temperature goes up, the K needs to go down because it won't want to go to the right as much. And so that pretty much means A is your answer immediately because this is going up, this is not changing, and this is just a red herring with an enthalpy diagram that's trying to confuse you. So A would be the answer. All right. Now we're getting on to Ksps. The solubility of MnIO32 is 4.8 times 10 to the 3 mole per liter, and you want to find the Ksp. All right, so let's give ourselves a little bit more space. Firstly, you want to consider how does this dissolve? Well, this solid, is going to separate into these ions. And so that's the dissociation. Now you know the solubility is 4.8 times 10 to the negative 3 moles per liter. So that means the concentration of MnIO32 is 4.8 times 10 to the negative 3. But considering that you've got this, one of these to give you one of those and two of those, that means when this occurs, the concentration of manganese will just be the same as the concentration of the compound, which is 4.8 times 10 to the negative 3. But the concentration of the anion, because it's 2 to 1, will be double that, which should be 9.6 times 10 to the negative 3. When it dissolves, it's 1 to 2. So as a result of that, what we now have is to calculate your Ksp, we know we need to take the concentration of the manganese ion times the concentration of the iodide ion, and then we have the numbers. And so with a little bit of calculator work, we get an answer of 4.61 times 10 to the negative 5, which is not what we want. So MnIO32, we give you Mn2 plus 2IO3 minus equals 4.8 times 10 to the negative 3. Oh, of course, I should square this, right? Of course, the Ksp should be related to your ratios. So this is 1 and this is 2. So you should square that. And once we square that, we instead get an answer of 4.42 times 10 to the negative 7. And once we get that answer, then it's the appropriate answer. Looks like it should be B. Does anyone have any questions so far? Okay, so here we've got hydrogen produced expression for equilibrium constant. I think that should be pretty easy. Okay, so I don't imagine those will be too much of a trouble. So we'll quickly run through this. Hydrogen is produced on an industrial scale from methane. The equation for the reaction is given. Expression for equilibrium constant for the reverse reaction. Well, if it's the reverse reaction, then just to prevent confusion, we'll write it out. Keep in mind that they're all gases. And now that you've written it out, you now have products over reactants. So of course, it's going to be CH4 times H2O to the power of 2 all over H2 to the power of 4 times CO2. Okay, so that's sort of doing it sort of by rote, writing it out and then doing it. Another way you could consider it, of course, is just work out the equilibrium constant expression for the reaction you already have, and then just take the reciprocal because your reactants and your products are going to switch around. So it's just going to be the reciprocal. But you're looking for the expression that we've got there, which looks like it's going to be A. Okay. If the temperature remains constant and the volume of the equilibrium system is halved, well, if you halve the volume at full constant temperature, then the immediate concentration of hydrogen, or any of the gases really, will of course increase. Because concentration is N over V, you haven't changed N, you've changed V, all of these are gases. So in fact, all of them will increase and double specifically. How will the concentration of lead ions in equilibrium with lead iodide be affected if the concentration of iodide ions were doubled? Well, we've got lead iodide. It is quite insoluble. It's therefore in a saturated solution with the lead ions and iodide. And so you're going to have a Ksp, which is going to equal Pb2 plus times I minus all squared. And this will be some number. It doesn't matter what this number really is. You can look it up in your data sheet because they're not asking you to calculate numerically what happens. They just want to know what happens. So if this equals some number, call it K, and we'll call this, let's say, M. So you've got lead times the original number of iodide ions, we'll call it M, equals K, or M squared, I should say. And now we're doubling the I. So that means your new lead concentration times doubling the M all squared equals K. So your new lead concentration times 4m squared equals K, which is the same, of course, as your old lead concentration times m squared. Which, of course, means that your lead concentration, your new one, is your old one divided by 4. And that probably made sense, right? You know, just without doing any calculations, that if the iodide goes up, then this will shift left, right? The Chichella's principle. And if it's shifting left, that means the lead ion will go down. So you already know it's not A or B really. It's just a question of which is the factor. Because of the square, then it will be a factor of 4. And so D will be your answer there. All right, so moving on to extended response questions. Here, you've got a reaction. And whenever the volume is not 1 liter, pay a lot of attention to that. Okay. The 2 liter container. And as expected, they did try to trip you up here because they give you a number of moles. We just talked about it earlier. Make sure you convert to concentration. They said using the data from the graph, determine the value of the equilibrium constant KQ for the reaction. So we've done very similar questions before, so I'll just do it very quickly. KQ, of course, equals AB2 all squared all over A2 times B2 all squared. That's your reaction. You just get that expression. You obviously need to get the concentration of each one at the equilibrium. So you can just read off the number of moles. This is 2, this is 1.2, and this is 0.8. But remember, that is the number of moles, not the concentration, which you will need to divide by 2 to get. So AB2 would then be 0.4 all squared. A2 would then be, well, 1. And B2 would be 0.6 all squared. And once you work out what that number is, that should be your answer. So it's 4/9. Okay, so at time of 15 minutes, some B2 was removed from the system. At 20 minutes, the contents was analyzed and the following data was obtained. Determine if the system had reached equilibrium at 20 minutes and describe the rates of the forward and reverse reactions at this time. Okay, so remember what we worked out earlier. We worked out that K was 4/9. So if K was 4/9, we basically now need to work out the reaction quotient Q. So we'll write our expression here. Okay, and we know that's meant to be 4/9. All right, with that in mind, let's now look at the data that they're giving us. Remember, adding or removing reactants does not affect K. The only thing that affects K is, well, apart from the reaction itself and the equation you're using, assuming that is set, the only thing that affects K is temperature. You can add as much reactants as you want. You can remove as much products of reactants as you want. K will not change. Same with any other reaction condition like adding or removing a catalyst, changing pressure, volume, and so forth. So we know K is 4/9, and we know at 20 minutes you have these concentrations. So we need to work out the reaction quotient Q using those numbers there. That gives us an answer that's clearly not 0.44, it's 0.536. So we'll note importantly, as we covered earlier, that Q is not equal to K. And specifically, Q is greater than K, because this is around 0.44. So if Q is greater than K, then we know that it is not, has not reached equilibrium. So that answers the first part of the question. The system has not reached equilibrium. And now we want to consider which way will it shift. And once we know which way it shifts, we'll be able to describe this. So if Q is greater than K, that means Q needs to go down, which means it needs to shift left. Now, if it's shifting left, what that means is, of course, the only reason it's shifting left is because the reverse rate is beating the forward rate. So it's greater than or equal to rate. And so we would say that the rate of the forward and reverse reactions, we would say the rate of the reverse reaction is greater than the rate of the forward reaction. And we should also say that they are not equal to 0. You should always try to stress that point about the rates. Even at equilibrium, the rates are not 0. So with this one, you have another equilibrium system again. It involves the oxidation of nitric oxide, 2NO gas plus O2 gas to give you 2NO2 gas, and it's exothermic. If the temperature was increased at time t, determine the effect of the equilibrium and then do the graph. So it is exothermic. You are increasing the temperature. If you're increasing the temperature, that means it will shift left or favor the reverse reaction. Now, if you have a reverse, that means, of course, NO2 will go down, NO and O2 will go up. Now, remember, when it's a temperature change, that means none of these concentrations will change at that time. They will all start from the same spot. That is different to when you add or remove a particular product or reactant, because that one will then suddenly jump up if you're adding it, or jump down if you're removing it. It is also not the same if you were doing changes in volume or pressure, because any of those changes would affect all the gases equally. Whereas in temperature, there's going to be no change at all at that particular time. Now we need to draw NO2 going down, NO going up, O2 going up. You should pay particular attention in the exam to the ratios. So I'm going to try to roughly do it by hand, but you should be using a ruler in the exam. So NO2 will need to go down by a certain amount. We don't know how much. So I'm going to, let's say, make NO2 go down by this much. So if NO2 is going to go down by that much, so I'm just going to give you an idea. We're going to have some lines. So they should all hopefully reach equilibrium at the same time. And NO2 should go down by this much. So that means NO, oh, sorry, that's not NO2 at all. NO2 is the further one. Okay, so if NO2 is going to go down, and I'll use a thinner line. If NO2 is going to go down, we'll probably make it, let's say, go down by this much. So it's going down by that much, which then means NO, because it's also a 2, and both of these are 2, should go up by this much. So roughly there, right? And O2, being a ratio of 1, should go up, but by about half of that. So roughly here, approximately. All right, so with all of that in mind, we then just try to draw it so that this will go up and meet here, this will go up and meet here, and this will go down and meet here. So something like this. Of course, once it's there, you want them to be just flat and horizontal. This question has no numbers on the axes, but if it did, you need to pay attention to that as well. So remember, when it's a change in temperature, there will be no major shift at a particular point in time. At the time of the change, there will be gradual shifts from the original concentration. We've already done entropy and so forth, so I think we'll skip this question. And here it is again. Let's find some, okay, so taking a look at this question. You've got a solution containing an equilibrium mixture of two different cobalt ions. So you've got cobalt. So you've got cobalt H2O6 2 plus, which is pink, plus 4Cl minus aqueous to give you cobalt Cl4 2 minus, which is blue, and 6 H2O. So you may not be aware, but this is actually used in your desiccants. So there are certain types of desiccants that change color. So a desiccant is something that absorbs water. And so those sort of silica gel kind of things that absorb water, often you want some indication of whether it's wet or dry. And so they may add some additives to it, of which this is one possible one that they could add, where that will change the color between pink and blue. Now, generally, they don't add it to ones that have food because cobalt is poisonous. And so they also develop other ones which change between green and sort of orange, which are sort of not poisonous. But this is the traditional one. Okay, so when the equilibrium system is heated, the color changes from purple to blue. Okay. So if you're going from purple to blue, that suggests, considering that you've got pink and blue, that you've shifted right. And it might make sense to sort of think about, especially, I mean, you don't need to know this, but it might sort of help. So when you heat it, this H2O, the water that is bound with the cobalt, is released, as the equation says. You release it. So the idea is this you can get rid of this water, okay? And then it's now going to be ready to absorb water to indicate, okay, when it's blue, I'm dry. When I absorb water, I become pink, I'm wet. That's the idea. Now, you don't need to worry about that. You just need to think, okay, for purple to blue, how does it do that? Well, it wasn't pink to blue, but purple suggests there was, some pink, some blue. And you've now shifted to the right. So that means because you shifted right, you expect COCl4 2 minus to go up. You expect COH2O6 2 plus to go down. And you expect Cl minus to also go down. Now, clearly, you don't think it's going to be something like A because, well, it doesn't. Shifts don't occur like that. Now, B, C, and D, well, the thing is, the instant the solution was heated is when the change occurs. So D has these changes, so it's not D as well. And then you're looking at between B and C. And if you look just very quickly and go, hey, COCl2 minus is going up. And you might say, hey, that looks okay. You're saying COH2O2 plus goes down, and you've got that one going down. And if we have Cl minus going down, both of those seem okay, just at first glance. So I want you both to take a look at that, and I'll give you 30 seconds. Type in the chat whether you would pick B or if you pick C. And you can also say, you don't know, but I want you to make a choice regardless. Imagine it's an exam, right? Okay, time's up. You all submit your answers. Okay, so looks like some of you are a bit unsure. So the key thing you really need to be looking at here, and the reason I'm asking because we kind of covered it before, you need to look at the ratios. Okay, so we have a bit of a debate. Now, basically, you don't need to worry about the H2O because it's not in the graph. But the thing is, COH2O62 plus goes down, and Cl minus does go down, but this needs to go down 4 times more than that. Those two need to be about 1 time, and the other one needs to be 4 times. So this is where your ruler may come in handy, all right? Now, Cl minus needs to go down 4 times. Now, I think many students might think, oh, well, that's a big drop. But remember, it's not about whether it's a big drop or not. It's about whether it's 4 times this or how much this went down. So and this really, I think, is where a ruler would come in significantly more handy. But you've got COH2O6 going down 1 times, and then you have this going up by 1 time, and quite clearly, the amount that this goes down and the amount this goes up, right? So if I trace it in a different color, the amount that this one goes up and the amount that this one goes down, even without a ruler, looks quite clearly different. But they're meant to be the same. They're both meant to be 1 times. And for that reason, C cannot be correct. If you had a ruler, we can compare these two. And this one going up and this one going down looks roughly equal, but a ruler would confirm that. Okay. And while it might not be immediately obvious, a ruler would also confirm that basically the chloride drop is going to be 4 times that distance going up. But the key point we're making here is you want to look at the ratios as we outlined earlier. So here, B would be the appropriate answer. All right. So we've talked about questions like 29 before. This one is just, so what I will just quickly make a note here. This question 30 here about the Torres Strait Islanders and Indigenous Australians processing the toxins is something you will need to know. It is a dot point. So you can just simply memorize your answer. Okay. So essentially, there are two main ones they can use. The more popular answer is basically talking about how you would prepare using the chemical principles. So we'll briefly run through this, but you can more or less just look it up in your textbook and memorize them. So we won't write out the full answer, but we'll just give you the sort of outline. We want to write an answer with respect to the chemical principles studied this year. You want to explain the scientific basis in the way Indigenous Australians process the cyan fruit to remove the psychosin prior to consumption, which is toxic. So we need to refer to the fact that this is soluble in water, and we can refer to its polar nature for that. Now, it's not particularly soluble, and you also need to talk about the processes. So the processes are, they will grind the fruit, and then they will place it in the middle of the stream, and basically allow water to flow over it over time. And so we need to make reference to the fact that it's soluble. Grinding increases the surface area and aids in having water getting to more surface area and therefore doing more solvating more. And then more importantly, as far as this question is concerned, the fact that we're placing it in the middle of the stream and allow water to flow is we would refer to the fact that basically it's an equilibrium system with a continual exchange of water so that the toxin can dissolve and then it dissolves into the water, but then the water runs, is washed away and you're replacing it with new water constantly. So the equilibrium is constantly being shifted into the solution side so that over a period of days or weeks, the concentration gets low enough such that consumption is no longer dangerous. So by Le Chatelier's principle, favors the solution of the toxin. And therefore that keeps reducing the concentration, which is the aim. Okay, so we've done a lot of these sort of questions. This is a calculation question. So we'll just take a quick look at 18, just because it's in reference to callus, which I haven't said a lot about. So you've added a callus to a system in equilibrium. Which of the following would correctly describe the effect of the callus on the system? Remember, very simple. A callus and equilibrium doesn't matter. Does not affect equilibrium. So definitely no shift. That's wrong. The key things to remember about a callus is it lowers the activation energy. So that one's wrong. It has no effect on equilibrium. So it's either B or C, of course. An effect on the forward rate of reaction. Right. So you've lowered the activation energy. So that means you've lowered the amount of energy required to get the reaction going, which means, by definition, what a callus does is increase the reaction rate. So a callus lowers the activation energy, which increases the reaction rate. However, it does not have an effect on the equilibrium. And the reason for that is not because that it doesn't increase the forward rate of reaction. It does, but it also increases the rate of the reverse reaction. So the catalyst will increase R1 and R2 equally so that they still are equal. And because the rates are still equal, then there is no effect on the equilibrium position. Okay. So let's go on to the other file now that you've also had, and let's do some calculation questions there. We'll continue working on this second file that we're sort of opening up now as well, just because tomorrow, because it sort of spills over into acids and bases. So today you'll be looking at your acids and bases and so forth. All right, so a bit more calculation heavy now. Got a certain temperature, KQ is 75. 0.3 moles and 1.5 moles were reintroduced to a 5-liter vessel. I mean, we've done similar questions to this, so I won't do it, but just pay attention to 5 liters there. Okay, arrange the following reactions in order of the increasing ability to reach completion. Remember, the bigger the K, the more likely it's to reach completion. So that's a pretty simple. Just all you need to do is look at the K value. I mean, and pay attention to the power. Don't leave that off, of course. And then rearrange from, well, if it's increasing ability to reach completion, then from smallest to largest. So of course, -5 goes first, then -3, then 18, then +7. So in that order, right? 4, 2, 3, 1. we've already done some questions like that, so we'll just skip that. All right, so let's take a look at 7. You've got iron 3 ions and thiocyanate ions are in equilibrium with the iron 3 thiocyanate ion according to the following equation. Now, you may or may not be familiar with this, but you would have come across it in module 8. All right. So the thiocyanate ion is one way to, well, it is the confirmation test for iron 3. You would add this, if you suspect you have iron 3 in your solution, you can add this thiocyanate ion, and it can, as this equation shows, form this complex ion. And the idea is that this has a blood red color. Now, you don't need to know that for this question, but you just had, they've already just given the equation, but it is something that you should know from your module 8. So the system is then put under increased pressure, and what will it cause? Take 15 seconds, give me your answer in the chat. So time's up. For people who haven't given me the answer, can you just quickly type one? Okay, so it seems that the popular answer here is C. And so the popular sort of school of thought is probably, hey, we've got one thing here, so total of 2 on the left, and one on the right. So increased pressure pushed to less moles to the right. And I imagine that's why many people are choosing C right now. But that is unfortunately not the right answer. And it's for that reason why I wanted to go through this question and get you guys to pick an answer first, because you are increasing pressure. Now, increasing pressure does push towards less moles, the side with less moles, but you might also want to remember that it's the side with less moles of gas. And in this case, it's an aqueous solution, and an aqueous solution, and an aqueous solution. So gas, there's no gases. So therefore, pressure doesn't matter, right? So the answer is D, okay? Because you have no gases, pressure affects gases. As simplistically, pressure affects gases. So if you don't have a gas, then don't worry about it. It's not going to affect anything as far as we're concerned. Okay. Now, you probably won't get asked this question that I'm about to sort of extend, but sometimes you do, and you certainly might see it in trials. So let me deliberately try to ask you a sort of similar question. So I'm going to take the same equation. I'm going to take the same equation here. Okay. And I'm now going to change what we're doing. So we're not increasing the pressure. But what I'm now going to do is I'm going to add water to the system. Okay. We add water to the system. And I'm going to simplistically just ask, what do you think will happen? All right. So you basically have 3 choices, right? Your choices are basically that if you add water, it will shift to the right. If you add water, it will shift to the left, or it won't make a difference. That's really your only 3 valid options here. So take a minute to think about it. And I want you all to make a decision, because assuming it's multiple choice, you have 3 choices. Make a decision. Even if you're not sure, make one. You've got about 40 seconds left. Either shift right, shift left, or nothing happens. And I'm more than happy for you to tell me if you're confident or not confident in your answer as well. Okay. So, excuse me. We have suggestions that it will shift right or that it won't change. So the thinking behind that it won't change is probably related to what we said earlier, that water is, well, a liquid, and liquids generally don't change concentrations and thus doesn't change the equilibrium. That's probably the typical thinking there. And note that I did say there were exceptions to that rule, right? So typically, yes, we say that if it's adding solid or liquid, then it's not going to change anything. But I did say there were exceptions to that. Now, someone said that they thought it would shift right. Was there an explanation for that? What was the thinking behind shifting right? Can you type up a quick idea? In fact, just say it might be faster. What's the... Kenny, what's your thinking for why it would shift right?
Yeah, because I thought that if you add water, the solution should be diluted.
Yeah. But why does it shift right then?
Because they got fewer number of moles.
So interesting.
I'm not sure.
So here's the thing, all right? When you add water to the system, you are going to dilute. Remember, these are aqueous solutions, right?
Yeah.
Because they're aqueous solutions, then they will all be diluted. So if you think about it in terms of as a concentration, all right, then basically what we've got is you've got Fe3 plus at some level, you've got SCN at some level, you've got FeSCN2 plus at some level. It doesn't matter. And the point is, when you add water, you're going to dilute all of them. So all of them will go down by some amount. I'm not going to draw it to scale. And if you look at this kind of looks very similar, right, in terms of effect to if I had gases and I increased the volume, right? So if I had gases and I increased the volume, they'd all go down as well, not drawing to scale. So when I add water to the system, it is indeed correct that I will affect the concentrations of all three equally by the same factor, because they're all aqueous solutions. When we said that adding liquid generally doesn't change them, that's generally because we're not usually changing concentrations, but adding water here will change the concentration of these because they are aqueous solutions. And basically, in a way, the volume of an aqueous solution is determined by how much solvent you've got, which is water. So essentially, you can treat this like a gas question where I'm increasing the volume. It's basically what we're doing, right? So the thinking is correct in the sense that when you're adding water to the system, you are diluting the solution. That is correct. But we dilute the solutions. But if you dilute the solutions, you're not only diluting this one, you're diluting all of them, which means, I mean, it doesn't make sense to shift to the right or shift to the left in a sense based on just one. So you are basically trying to shift kind of like a gas to the side that has more moles. On the left, there's 2. On the right, there's 1. So actually, the answer to this will be shift to left. Now, to be perfectly clear, this question is usually not tested. Yeah, not saying it's impossible, but usually it won't be tested. So this was sort of a bit rarer, but I just thought it would be a good opportunity to bring this up because you probably haven't come across it before. And, you might see it in certain trials and things like that. Okay. And the other option, in case, if you're not happy with this sort of conceptual way of thinking, then your other option is just to go with K, right? Write out the expression for K, make all of them go down by half, for example, and you'll find that the shift is going to then go left. So this one, I think, well, we can skip because we already have answers there. All right, so this is now talking about Ka, which we might leave till tomorrow. It's related to, so we've got some stuff here on acids and Ka and pKa. We've already done this one, I think. So it looks like there's a bit of overlap here. All right, we want to now do a few more questions here on the common ion effect. So because I've already written a solution here. We won't go through that question. You can sort of do that. We've already gone through that one. Oh, well, let's see. There's surely. I mean, most of this is now K and Kb. All right. In that case, does anyone have any particular questions that you want to ask at the moment? No questions? Okay, then if you have no particular questions, we'll get a start on Ka and Kb, which we'll be doing tomorrow anyway, and it's related to your equilibrium constant. And then tomorrow we'll just review everything from acids and bases as well. If you did have any questions, please write them down and let me know. And similarly, when you're reviewing tonight, if there are any particular questions, do let me know. You can put it in an email and email it to me, and I'll try to address it in the first 30-40 minutes of the lesson during our review. And that way, and it's similarly for the homework. All right. Now tomorrow we'll cover acids and bases, which will include K and Kb. But remember, Ka is basically representing the strength of an acid. So basically, we know that if you've got Ha, where A represents an acid, then simplistically, it will ionize fully or partially, depending on if it's strong or weak, to H plus A minus. So when you work out your Ka, it's basically the same thing as your equilibrium constant, except applied to the acid dissociation equation, which we've written out. So it'll be H plus times A minus over HA. So here we've got Ka equals 6.6 times 10 to the negative 4. Given that Ka times Kb equals Kw, and Kb of hydrofluoric acid is calculated to be that, then very easily we can just get Kb equals Kw over Ka, which you can either know or look up in the formula sheet is 10 to the negative 14 over 6.6 times 10 to the negative 4. That presumably is going to give us A. So remember, K represents how complete it gets. So the greater Ka is, then the more complete the dissociation / ionization, and therefore the stronger the acid. Here, you've got the concentration of hydroxide ions in mole per liter in a solution has a pH of 9.54. So your pH is 9.54. You might recall that that is, well, negative log base 10 of H plus. Now, it may be helpful and more quick to just work out POH. Remember, pH plus POH equals 14. So POH would equal 14 minus 9.54. which means it's 4.56. And then, of course, to get from there to the concentration of OH minus is just going to be 10 to the power of negative 4.56. Which is 2.75. That is interesting. If the pH is 9.54, then it should have been 4.46. 4.46. And giving you an answer of 3.47 times 10 to the minus 5. So that then means B is the answer. Okay, so I'm not sure why this question is here, but a buffer, which we'll review again tomorrow, can be made by mixing a conjugate acid and a conjugate base, and its conjugate base, it has to be weak. And so clearly, carbonic acid, while it's a weak acid, is not paired with its conjugate base, so that would not be A. Nitric acid is a strong acid, so that's out already, even though it is paired with a nitrate. Now, ethanoic acid is a weak acid. Ethanoate is, well, the base, so that one looks okay. Hydrochloric acid, of course, is not okay, being a strong acid, which means the appropriate answer there is C. Now, the conjugate base of hydrogen sulfide, to get the conjugate base, you simply remove an H plus, so that makes it 2 minus, and therefore the answer will be SO3, 2 minus. This really doesn't have too many equilibrium questions here. Let's focus on those. So you've got pKa. So remembering that pKa is just minus log base 10 of Ka. So in your course, you'll come across things like pH, pOH, pKa, pKb. Just remember, when you have that P, that represents power, which mathematically is negative log base 10. Okay? So whenever you see a P in front of something in this context, then we're basically saying we're taking negative log base 10 of that thing. Okay? So we've got a pKa of chlorous acid is HClO2 is 1.96. And nitrous acid has a pKa of 3.39. So when comparing these two acids and their conjugate bases, the relative strength of each acid as conjugate base can be identified as, well, pKa is 1.96 and 3.39. And you've got HClO2 and HNO2. Now, what may be confusing for some students is that the pKa and the Ka, because of the minus log 10 relationship, is not the same, in the sense that, think about it in terms of pH, right? The lower your pH, the more acidic your acid is. But that also means the higher the concentration of the H plus ion. So similarly for pKa and Ka, the lower pKa is, the higher the Ka is. And we can prove that by working it out, if that's helpful. So Ka is 10 to the power of negative 1.96, which gives you an answer of 1.1 times 10 to the negative 2. And the Ka of that one is 10 to the power of negative 3.39, giving you an answer of 4.07 times 10 to the negative 4. So if you're not comfortable with working with pKa, then just convert them to Kas. Okay? And it should be quite clear that this is a stronger acid and this is a weaker acid. Now, once you've established which acid is stronger and which acid is weaker, then from your acids and bases theory, you should also know that the stronger the acid, the weaker the conjugate base. So your conjugate bases are ClO2 minus and NO2 minus. Because this is a stronger acid, that means this is a weaker conjugate base. And this would be a stronger conjugate base. So with that in mind, we should be ready to pick our answer. So the stronger acid is HClO2, and the stronger conjugate base is going to be NO2 minus, being B. I've already done that question. I think did we not already do? Somehow we went back up, I guess. No wonder there seemed to be a lot of repetition. Let's find one that are related to. Okay, so let's look at this one. Because it is going to have an equilibrium involved. Okay. So we've got hydrofluoric acid is a weak acid, hence it means it's equilibrium. The pH of a 0.025 molarity solution of hydrofluoric acid is 2.39. Now, you want to calculate the Ka. So we need to firstly understand that HF partially dissociates to H plus F minus. Now the Ka is, of course, the concentration of H plus times F minus, all over the concentration of HF. Now we know pH equals 2.39, but that means that the concentration of H plus is 10 to the power of negative 2.39, which as a number is 4.07 times 10 to the power of negative 3. Now, what you also know is that the concentration of this solution is 0.025. So what that means is that the concentration of HF should be 0.025. Now, of course, if HF is at 0.025 and some of it dissociated, then using your sort of ice table is not exactly 0.025, right? So if you started off with HF and you have H plus and F minus, so at the start, you're saying it's 0.025 and this is none. And then we're saying that this is 4.07 times 10 to the negative 3. By your ratio, this is going to be also 4.0 times 10 to the negative 3. Then this one really wouldn't change much, right? But I mean, since we have the numbers, we can take it away. And that gives us our end. And we can get an answer of 2.09 times 10 to the negative 2. And then we can sub it into our expression above for Ka. And that's going to equal 7.93 times 10 to the negative. Of course, once we've got Ka, then getting pKa is very easy because pKa is just negative log base 10 of Ka. So that gives you an answer of 3.1. Now it asks you to calculate the percentage dispersion of the hydrofluoric acid, which means we would need this Ka. Now, we know the amount, right? Like if it dissociated 100%, then this would go to 0 and this that. So I guess the percentage dissociation, like for every one of these you lose, and for every HF molecule you lose, you get 1 H plus. So the percentage dissociation would really just be the 4.07 times 10 to the negative 3, the amount that did dissociate, over the total amount. And that gives you an answer of 16.3%. So that also gives you some idea of how well weak acids, or how not well even, weak acids dissociate. Because to be clear, hydrofluoric acid is a weak acid, but it is an extremely strong, out of the weak acids, is a very strong weak acid. So 16.3% is very high as far as weak acid is concerned. Many weak acids are at the 1% or even less. So most definitely when we talk about a weak acid, we're saying that there is some amount of dissociation, but it is significantly lower than the ones that don't dissociate. Because even for a pretty extreme weak acid like hydrofluoric acid, you're still looking at 4 that didn't dissociate to every one that did. So it's certainly in the minority. Okay. Let's see if we can find one that's on. These are all values Ka. A very similar question. Okay, so let's do question 27. That's from the HSC paper. And calculating pH from values is something that people struggle with, but it really does relate to your equilibrium constants and so forth. So the relationship between the acid dissociation constant Ka and the constant Kb, we've already done this in an earlier question. So show that Kb of the hypochlorite ion is OCl minus. All right. So Kb is simply Kw over Ka. And you can just simply put in your numbers, 10 to the negative 14, over your Ka of 3.0 times 10 to the negative 8. And that will give you your 3.3 times 10 to the negative 7 as required. Now, the conjugate-based dissociation constant Kb is the equilibrium constant for the following equation. So they've written out the equation for you, which is very nice of them. And we already know this Kb equals 3.3 times 10 to the negative 7. You now want to calculate the pH of 0.2 mole per liter solution of sodium hypochlorite. Okay, so if you've got a 0. Just to do it step by step, if you've got sodium hypochlorite, which is a soluble because of sodium, the first thing is that it's going to dissociate into sodium and your hypochlorite ion. So if you have 0.2 mole per liter of sodium hypochlorite, then you're going to have 0.2 mole per liter of hypochlorite ion. Now, that 0.2, that hypochlorite ion will react with water and partially, dissociate. Well, react with water to form some OH minus and some HOCl. Now, how much does this go across? Well, we'll have to use the Kb to work that out. So let's do our ice table. So we've got OCl minus, which starts at 0.2. H2O we don't really need. It's, and we've got H because it's liquid, it's not part of our expression. So to be clear, this expression is going to be HOCl times OH minus all over OCl minus. So we will need to know the other two. And we'll assume they started off at 0. Now, when there was a change, some must have dissociated to the right, which means you're going to lose some amount, which is unknown. But because, and keep in mind, you've got to keep the ratios in mind. All of this is 1 to 1 to 1 to 1. So you're going to lose some amount. So those will gain some amount. So you're going to end up with 0.2 minus x here and x there. Now, that means this expression will then become x squared over 0.2 minus x equals this number, 3.3 times 10 to the negative 7. So in other words, you're trying to solve x squared over 0.2 minus x equals 3.3 times 10 to the negative 7. Now, you could, multiply this out, solve the quadratic, and so on. But in chemistry, we're often used to approximating. And the thing is, this x is the amount that dissociated, and we just said that this is going to be a very small amount. So we assume that x is significantly smaller than 0.2 in this case. In other words, 0.2 minus x is close enough to 0.2, and that simplifies our calculation significantly. You can, of course, do this without doing the simplification, but that's not what they expect for you to do in the HSC. And of course, you'll find that if you were to do it, your answers won't change by all that much. So it will be within the margin of error that they're willing to accept. So that means your x squared will end up being 6.67 times 10 to the negative 8, which then means that x is 2.58 times 10 to the negative 4. Remembering what x is though, x happens to be the concentration of hydroxide. So we have at this point worked out the concentration of hydroxide is 2.58 times 10 to the negative 4, which lets us work out POH by taking the negative log base 10 of that, which is 3.59, which of course lets us get the pH, which will be 14 minus that, which will be 10.4. And that would be your answer to this question. And that's how you do it. Okay, so I'll be sending you an email with the new worksheets that you can work on for tonight, as well as some more things to review.